everyone, welcome to my colour chemistry series. Today I'm going to be talking about not the Phantom of the Opera but the secret of the opera, the rose of the opera, Opera Rose. It has an interesting secret in the way it's manufactured that is what gives it that wonderful ethereal quality when it's viewed under natural light. To explain, it actually only officially, if you look on the side of the tube, contains one pigment, and that pigment is this one here. Let me find something I can point with. I'm so well organised. Is pigment red 122 quinacridone red. Don't get confused, there is another quinacridone red with another code, so don't worry about that. It's also the same pigment used in quinacridone magenta in the Winsor & Newton professional range, which is 545, as well as Opera Rose 448. So if they've both got the same pigment and that's the only pigment declared, how come they're so different? If you look at them, you can see Quin red is kind of a dull pinky red, but there's this wonderful brightness which the camera does not do justice to with Opera Rose. What's that all about? It's actually because there's another ingredient that is not really declared, and that is an additional dye, which is BV Basic Violet 10, which is, if I can get my tripod to work properly, yay, there we go, which is rhodamine 6B. Rhodamine 6B is something you may have experienced sometimes at the opticians where they put fluorescent drops in your eyes. If you've had yellow ones, that's fluorescein, and you might have had pink ones, which could be rose bengal, it could be rhodamine, and they then view them with a slit lamp and an ultraviolet light and it glows. And that's exactly what it's doing here. This basic dye is actually bound into the pigment, into the binder, sorry. So it's not the pigment part of the paint, the actual gum arabic has been dyed using rhodamine 6B, which binds into the pigment. So that's why they don't declare it in the ingredients of the paint, because it's just part of the binder. And if you look on older tubes of Opera Rose, it actually used to say pigment red 122 and a fluorescent binder. And that was how in the 1950s, when it was invented, they got away with doing it as a trade secret. They hid it as part of the binder. It was never officially a pigment in the paint. So that's the official secret. But how does it actually work? Well, the secret is that rhodamine 6B is a fluorescent dye. So let's just do a little comparison here. Then I'll explain what fluorescence actually means. I'm going to use an ultraviolet LED torch here, and I'm going to shine it first of all on the paper. That blue glow that we're getting back is because there are whiteners in the paper, and they are also fluorescent, and they emit a blue light when hit by UV. Very, very faint normally, but that gives the impression that the paper is sort of whiter than white. And you can really see it on this acrylic paper that I've got here, whereas if I shine it on normal white surfaces I wouldn't get anything back. So you can see the acrylic has got much more brightener in it than this watercolour paper has got. And if I shine it over here, all you get is the purple glow of the fluorescence of the paper. But if I shine it on this Opera Rose, you get a pink fluorescence, beautiful vibrant pink fluorescence. But can you see it's not uniform? Can you see there are patches? That's because the binder has actually been dyed with rhodamine, and the patches where you can't see the pink fluorescence, where you can just see the magenta, are where you can only see the pigment. You can only see this dye up here. You can't actually see everything that's going on here. So that is how the paint looks so different. It contains this fluorescent dye. And under strip lighting, fluorescent lighting, or natural lighting, sunlight, there is always some UV. So that's hitting it and giving off a tiny, tiny, tiny amount of that fluorescence, which gives us the impression that it's this much brighter, more vibrant pink. Clever, huh? So how does fluorescence work, and what really is fluorescence? Quantum physics time! I'm going to explain fluorescence in really basic terms, not to patronise anyone, but just because quantum physics, let's face it, is not the most interesting subject, but I'll keep it really straightforward. Every atom that exists contains electrons. This is how we write them, in little e with a minus sign. They're a charged particle, doesn't really matter what they are or what they do, but all you need to know is that they live effectively on shelves. So let's imagine some tennis balls and they live on a series of bookshelves. But you're only allowed to put them on a certain shelf based on how big they are, let's say. Now, electrons in real life are all the same size, but they can carry different energies. We're going to analogize it and we're going to say size. So let's say this is how it works. Let's say ping pong balls live on the bottom shelf and Slightly bigger tennis balls live on this shelf, and footballs live on the top shelf because they're really big. Straightforward. You can only put them on the shelf where they're the right size. So I would not be allowed, if I put a football on this shelf, it would not be allowed, and I also wouldn't be allowed to put a ping pong ball on this shelf. Now here we have got a tennis ball electron. It's on the middle shelf, and I've arbitrarily numbered the shelves 1, 2 and 3. So it lives on number 2, and number 1 is the big shelf. If ultraviolet light, which is what I just shone on our dies here, hits the electron, it, in our analogy, it temporarily gets bigger. Now in the real world, what it does is it gains a bit of extra energy, but we're analogizing, let's say it gets momentarily big enough that it's the size of a football and it can live on the top shelf. So it immediately, being a social climber of course, it gets bigger, it jumps up to the top shelf because it's like, hey, I'm a football now, I can live on the top shelf. But that little bit of energy that allowed it to get bigger is transient and it goes away very quickly. So the moment it lands there, it has to leave. So immediately, the moment it gets there, it drops back down to where it belongs. And the energy that got it there in the first place has to be released. But the light that leaves isn't the same colour, the ultraviolet, that went in. The light that leaves is pink. And there's reasons for that, and I'll explain that when I talk about wavelengths and so on in another video. But that's why fluorescence works. You shine on a light at one wavelength, doesn't have to be UV, it could be a visible wavelength, and it comes out another wavelength. Wavelength just means colour, okay? So we're shining on ultraviolet, and what's coming off is pink. And that is how it works. I've put here a sample of an acrylic paint, a fluorescent green acrylic paint from the System 3 range from Daler and Rowney, and it's called fluorescent green, and it contains the pigment fluorescent green 8. If we look at that under ultraviolet again, remember the paper has just got that blue glow. Ultraviolet, incidentally, doesn't really show up. The camera picks it up, which is what that sort of white is. But I'm looking at these bulbs in real life and I can see nothing. So that's just the ultraviolet switched on. I had visible on as well before. There's the ultraviolet. It looks blue or white on this camera because the camera is actually able to see it, but the human eyes are not. You can't see a beam, but there you are. That blue is the fluorescence of the paper. I'll remind you, over here, slightly less fluorescence. Shine it over here and look at that beautiful bright green glow coming back. It's so bright the camera can't cope with it. The camera's totally overloaded. But I can assure you the colour that's coming back is a vibrant yellow-green. If I move this further back, yeah, there we go. Really vibrant yellow-green fluorescence coming back in return. I'm just going to turn off the light that's above me. Well, there you go. Now we're doing it in near darkness. I haven't got a light above me to confuse things, and you can really see it. Really, really, really violent fluorescence. Let's look at the Opera Rose now. Wow, look at that. You can really see the fluorescence of the Opera Rose now. I've got no lighting above. But the Quin Red, absolutely nothing. So that's how Opera Rose works. That's how fluorescence works. Thank you very much for watching. I hope you enjoyed this and my other colour chemistry videos. Goodbye.